All right, hi everyone. So today we're going to work on probability and actually find probabilities based on the type of probability that you're looking at. So there are different types of probability that we're going to learn. Plus, we're going to talk about the law of large numbers, and we're going to use that fundamental counting principle that we talked about the other day to find probabilities. Okay, so let's take a look at the different types of probabilities. There's classical or theoretical probability, used when the outcome in the sample space is equally likely to occur. Think of this as what should happen, okay? So this is when we can write a sample space and we look at the theory behind it. So when I roll 2 dice, what are the outcomes? When I flip a coin, what are the outcomes? These are things that we can theoretically look at. So this is what we're used to thinking about probability. It's the number of times something happens over the total number of times. So if I roll a die and there's 6 things that could happen, I want to know what is the probability of getting a 3. There's 1 out of 6. Okay, that's the typical probability that we're used to. Where empirical or statistical probability is based on observations obtained from a probability experiment. This is when we're physically doing an experiment and we're looking at the probability. So there's some form of experiment happening. Okay, this is when I physically roll a dice and collect the information, or I pull red, white, and blue poker chips out of a bag. What's the probability of getting like a red or something like that? And I perform an experiment. So these are things that we look at in terms of like going out and physically doing something. So it's how many times the event occurs over the total number of times you do it. Okay? Now there's also the law of large numbers. And this is what eventually happens, is if you do an experiment over and over and over again, the empirical probability, which is this guy, will eventually be the same as your classical or theoretical probability. So if you toss a coin like 10 times, in theory, you should get 5 heads and 5 tails. But in real life, that's not what happens. So what you have to do is, if you do that thousands of times, like in our graph here, eventually you'll get 50-50. But the smaller number of times you do it, the less likely you are of getting the actual theoretical probability. So when you're doing an experiment, that's why we do things over and over again, to get the theoretical probability. All right, so that's kind of like the idea here. So the more times you do it, the closer it becomes to a theory. And then the last type is called subjective. We usually don't like to talk about subjective because it's an opinion. There's no math or behind it. It is just based on observation, educational desks, and estimates. Okay, so it's kind of like, can you write a sample space? No. Can you do an experiment? No. Then it's subjective. All right, so let's take a look at some problems involving both theoretical and experimental. So the first one, let's call this our theoretical or classical, right? Classical. I always get those mixed up. So we're going to do this. This is a classical probability. Okay, how do I know? Because I'm going to roll a 6-sided die and I'm going to write a sample space. So when you write a sample space, that's theoretical. That's the classical or theoretical. So I'm writing 1, 2, 3, 4, 5, and 6. And I want to find the probability of event A. Okay, event A, that's probability of event A is rolling a 3. So there's only 1 3 out of 6 of them, so it's 1 6. Probability of rolling a 7. Well, there are no 7s. So probability of event B is 0 out of 6, because it's just not going to happen. We don't have any 7s in our sample space. Rolling a number less than 5. So less than 5, and we're not including 5, 4 to 1, so there's 4 of those out of 6. You can write that as 2/3. You can write it as 0.66. You can write it as 66%. Any of those are acceptable. Again, that's classical or theoretical because we wrote a sample space and found probabilities based on that. But if you go out and collect data, if there's data involved, then this is empirical. Okay, or experimental. Because you survey a sample of 1,000 employees at a company and record the ages of each. The results are shown in the frequency distribution. If you randomly select another employee, what's the probability of employees between 25 and 34? Okay, so we're going to look at the 25 to 34-year-olds. There are 366. Probability of 25 to 34. There are 366, so that's the frequency of the event, over the total frequency, which is 1,000. You can leave it at that or write 0.366. Either one of those is acceptable. So notice there was an experiment. We went out and gathered data, and that's why we can be able to do empirical. All right, let's see if we can tell the difference between empirical, subjective, and classical. All right, the probability that your phone ringing during dinner is 0.5. So the question to you is, can you do an experiment? Can you write a sample space? Or is it just observation? If you said subjective because it was an observation, you are correct. Okay. The probability the voter chosen at random will be vote Republican is 0.45. Could we do an experiment? Could we write a sample space, or is it just our opinion? Well, you can do an experiment here. You can poll or question a sample of voters and determine the number of Republicans. So this is empirical. Okay. And the probability of winning a 1,000-ticket raffle with one ticket being 1 out of 1,000, this is theoretical or classical because we can write a sample space. We would have 999 no's and 1 yes. Okay. All right, now there's some basic rules of probability. So in other words, the range. Probability of an event is always between 0 and 1. If you got something more than 1, you're wrong. Okay, you probably divided it upside down. So that means that the probability of an event is always between 0 and 1, where if you get close to 0, it's probably not going to happen. But if you get close to 1, it probably is going to happen. So if you get 0.5, it could go either way. All right, so closer to 1, it's probably more going to happen. Closer to 0, probably not going to happen. And then you have the complement of an event. Okay, so the set of all outcomes in a sample space not included in the event. So a complement in an event is denoted by E prime, okay? Or I usually refer to it as E complement. So I have this little graphic here. Hopefully it'll help us understand. All right, so the probability in an event is E, so that's this guy here. And then E prime is everybody not in E that's in our sample space. Okay, so let's say that my sample space is rolling a die, 1 through 6. And my event is evens. So that means 2, 4, and 6 are in my event, and 1, 3, 5 are not in my event. So this is 3 out of 6. Okay, so that's just these guys. Now, E complement is what's not in, I should probably choose a different color, in the event. That's these guys out here. So probability of E complement or E prime is also 3 out of 6, just because I chose that. And together, if I put the event with the complement, I should always get 1 when I add them together. So 3, 6 plus 3, 6 is 6 over 6, or 1. So the complement is everybody not in the event. Okay, so could we do that the probability of the complement, or prime, is 1 minus the event? Yes. Okay, so keep that in mind. So we're going to use the distribution from example 2 to find the probability of an employee who's not between 25 and 34. So probably not 25 to 34. All right, so that's the complement of 25 to 34. All right, everybody not in the event. So if I come back up here, everybody who's not in the 25, so there's 366 in the event. So I could do 1 minus the 366 over 1,000 and get the complement. I think that's right. Yep, okay, I didn't do bad math. Okay, so 634 over 1,000. Now, could we have added everybody up except the 366? Yes, but that's not always going to be available to you, so think of it as 1 minus the event. All right, so now we're going to take all this stuff and let's see if we can do some applications. So the probability of experiment consists of tossing a coin and spinning the spinner. The spinner is equally likely to land on each number. Find the probability of each event. Okay, so this is, I think we can write a sample space for this. So that might be work. Let's write a sample space. All right. Okay, so we're going to toss a coin, so that means you can get a head and 1, head 2, head 3. Okay, I always write too big. Is that it? All the way up through 8? Yep. Oh, not done. We just did heads. We have to do tails. There we go. There's our sample space. So event is tossing a tail and then spinning an odd. All right, so we're going to toss a tail. So we want a tail and odd. Okay, so let's find tail odds. So this is odd, this is odd, this is odd, and this is odd. So there's 4 out of 16. 0.25 if you wanted to make a decimal or percent. Okay, event B is tossing a head or spinning a number greater than 3. Okay, so let me get rid of these guys. Okay, so we want a head. That's all of them. And greater than 3. Well, I already have some greater than 3s with the head, so I guess I don't want to add those in there. I would count them twice. Is it greater than 3? So we're not including 3, so that's these guys. Okay, so that's 13 out of 16. Or you could have done 1 minus 3. 1 minus 3 over 16. All right, so let's look at this. Your college identification number consists of 8 digits. Each digit can be 0 through 9. So how many digits do we have? We have 10. And each digit can be repeated. What is the probability of getting your college identification number when you randomly generate 8 digits? So I guess we have to figure out how many things in the sample space. So we have 8 digits. Each one has 10 choices. So we're going to multiply them together, hence the fundamental counting principle. So that's what? 1 million, 100 million? There we go. And we want to know probability of getting your ID. Well, there's only one way your ID could happen out of, there we go. So if you're guessing your ID, that's probably not a very good chance that you're going to get it right when you're just guessing. All right, let me know if you have any questions, guys, and I'll talk to you again real soon.